Good morning, everyone. I'm going to be your host today. We're just going to wait a couple more minutes just to get everyone settled in. If you guys have any questions while you're waiting, feel free to go ahead and drop in on the chat. Yeah, and we'll get started in 5 to 7 minutes.
Take notes.
You ready to go ahead and get started, Carly?
Yeah, I can. Just want to let you guys know, my name is Carly. I will be your host. I do marketing and events at Enertech. Just during this webinar, I just encourage everyone to take some notes. John will be covering a lot of items. If you have any questions throughout the webinar, if you look on your little menu bar, there should be a chat option. Go ahead and type your question in there and we will get to it whenever we can. And then it's always great to submit as many questions as you can. So feel free to submit anything that you need. If we don't get them all answered, we'll reach out to you after the webinar. And then if you need to leave at any time, you will be getting a copy of the webinar sent to you via email, and it will be uploaded to our YouTube page. So don't feel like you're missing out on anything because it will be available to you. Yep, and then we can go ahead and get started.
Alrighty, thanks, Carly. I appreciate it. Again, guys, the recording the training will be recorded, so you can go back and look at it. And if you have any questions at that time, you can definitely email me. My name is John Pendleton. I'm the trainer. I do a lot of site visits as well. So I'm a service technician, just like a lot of you guys are. That's where my background is. So I try to make our trainings a little, service technician, because that's my background. So I've worked on, everything from little bitty mini splits all the way up to, big factory jobs. So I've seen a lot of things in my career, and the last 7 or 8 years just solely on geothermal. So especially Enertech equipment. Obviously, I hate to say it, but I'm pretty much an expert on the geothermal Enertech equipment. So it's all I do every day. And this heat of extraction rejection that we're going to be going through, it's a key part in how we diagnose the equipment. So in today's training, I set it for 2 hours. I doubt that it'll go that long. It'll probably be closer to an hour, but I just wasn't quite sure on the webinar, so I decided to make it for 2 hours just to cover my bases. So we may get done a little bit sooner than that today, and if we do, I guess that's a bonus. But again, it's going to be recorded. If there's any other training materials you are looking for, if you actually want the slides, I can send you a PDF version of this as well. So just shoot me an email. It's the best way to get a hold of me right now. I am in the office today, but normally with this virus thing going on, as I'm sure you guys are all aware, a lot of us are working remotely. So I am working from home now. My phone is forwarded to my phone at home, but if for some reason I don't answer that, email is probably the best way to get a hold of me. So there's my email address. Feel free to reach out to me for any of your training needs. If there's other webinars you're looking for, let me know and I can make them, or if we already have them scheduled, I'll lead you to sign up. I did go ahead just on Monday, put a bunch more trainings on our Enertech University site. So definitely check it out, maybe weekly, because as some trainings get done, I will add more. Right now, I've got solar trainings booked out through the end of April, and I've got, I think, some lockout boards and other control boards type stuff coming up next week, and then some flow center stuff the week after that. So I've got a little bit of stuff all kind of laid out for you guys, and hopefully you can try to attend as many of those webinars as possible. If these webinars go well, this may be the route that we end up taking for long term. Not saying that we won't do online or in-person trainings, but like to do more of the online. So I'm sure we'll reach out to all you guys once things kind of settle down a little bit and get kind of your input on what you think of the online trainings. So we'll go ahead and get started. Again, heat of extraction, heat of rejection. If you subscribe to we have a YouTube channel, Enertech University. You can subscribe there, and we have a bunch of videos. We actually have a video on heat of extraction, heat of rejection, and again, all of our solar trainings, all that stuff. There's videos on there. There's videos on troubleshooting a reversing valve and how to troubleshoot a TXV and flushing a loop field, things like that. So check out those videos. And again, we try to upload our trainings to those going forward now too. So you will see some training videos on there. So with heat of extraction or heat of rejection, basically, there's no refrigerant gauges needed. You chose a pair of refrigerant gauges here, and you don't need to use those to figure out the heat of extraction or rejection. Now, the heat of extraction is what the heat that you're pulling out of the loop field to put into the home, and heat of rejection is what you're putting back into the loop field from pulling from the home in your cooling season. The calculation is the same. It's just called something else when you're in cooling versus heating. Again, verifies equipment performance that is either being rejected or extracted from or to the loop field. Basically, you'll need a water pressure gauge. I like to use a digital pressure gauge because sometimes we get into some smaller units, little half-ton units that have maybe drop, and it's kind of hard to read on an analog gauge. So we offer a Dwyer gauge. You can purchase it from us. You can also go online. Originally, when I purchased mine, that's what I did. I went online and bought it. Make sure when you buy that gauge or any gauge, you have to get the needle for it as well, because they normally don't come with the needle. And I would recommend getting the thinner needle, not the real thick one, because it'll insert into those pressure temperature ports a lot better. You'll need a digital thermometer. You can use an analog, I guess, it's a little dial, but I would recommend a digital. We have a Cooper thermometer that we sell as well, but it's got what I like about it, and I'm not trying to just promote our products. It's because I found these things and then we started to sell them. We didn't sell them before I got them. So we've got this Cooper, and it's got a tapered end on it, so it'll really slide into those PT ports a lot easier. We used to give away a thermometer here when you come to our trainings, and you put it in that PT port, you go to pull it back out, and the head and the wires would come out, and the metal shaft would stay in the PT port. So you have to grab your channel locks and pull it out and then pinch it and everything else. So we don't even hand but again, that's a Cooper thermometer and a Dwyer digital pressure gauge. Basically, once you get some information, you're going to compare it with the numbers in the factory catalog. That's why it's important to have the manual when you're performing this measurement. If for some reason you don't have a manual or you don't have a phone where you can download it, definitely call tech support. We can pull up the manual for you. We can send you a manual, or we can run the calculation for you real quick and check the specs. But the number you get on the calculation, you have to compare it to the number that's in the manual. And we'll cover that obviously as we go through this training. Obviously, we've got to have pressure temperature ports. You call into tech support. One of the first things we're almost always going to ask you is your water flow rate. And if you tell us, well, I don't have pressure temperature ports and it's on a pressurized flow center, there's no way to establish water flow. And we have to have water flow before we can really do anything. So we want to make sure that whenever you're installing a unit, that you always install pressure temperature ports. If you've got a water-to-water unit, make sure you're putting them on the source and the load water piping, because we'll want to check water flow on both. So when in doubt, put a pressure temperature port in. They're cheap and they'll save you. Again, if you don't have them, you call in. The only way to really establish flow is to drain the water leaving the unit into a 5-gallon bucket and time it to see how long it takes to fill it up. So that's why pressure temperature ports are super important. Non-pressurized, because we can use a flow meter tool to check that. But on a pressurized system or a pump and dump open loop, those definitely need to have pressure temperature ports. Always check the unit when it's in second stage on dual capacity units. A lot of our manuals do have part load information, but we would recommend second stage and turn the desuperheater off. The desuperheater will normally rob somewhere, it could be 3,000 to 5,000 BTUs. So our manuals don't normally show the information with the desuperheater running. So I'd recommend turning the desuperheater off. Or if it doesn't have a switch, you can just unplug the Molex harness for the high voltage to the pump. So we've obviously got to understand the engineering data tables first before we really go digging into pulling out the information, because you got to understand how to read it. In our manuals, this is a spec chart from, this is a 036, probably a packaged XT unit, more than likely. But you'll see we've got entering water temperatures, and that's just that, the water that's entering the heat exchanger on the source side. The newer manuals are a little bit better. We break it down into smaller temperature increments. On this one, it's just showing 30, 50, 70, 90 degrees. And you've got heating capacities on one side, and normally you'll have another chart next to it for the cooling. So your heating and cooling will be all on the same page. But entering water is just that. This is your coaxial heat exchanger. It's just EWT, your entering water temperature. Flow rate. When you pull up this manual, don't just say, well, I should be moving 5 GPM, so we're going to choose 5 GPM. one thing that's really important about this manual, we've got to have the manual because we have to compare the pressure drop that we get with our pressure gauge to the chart. And that will tell us the amount of GPM that the unit is running. I don't have a mathematical calculation to where I can just go, hey, I've got a 2-pound pressure drop at 50 degrees. Is there a calculation that tells me what that GPM is? The answer is no. They actually figured out, engineers figured that out in the lab. So that's why it's so important to have this manual. So again, flow rate is normally calculated, a gallon per minute. Normally on a system closed loop, we look for 3 GPM per ton. So 3 gallons per minute per ton. So a 3-ton unit, full load, you would want 9 GPM. Closed or open loop, we can go down to about 1.5 GPM because we have a more consistent water temperature about about 50 degrees. So PSI pressure drop, that's what we're going to ask you when you call in the tech support. We're going to take your pressure gauge, take your pressure in, and take your pressure out, and do the math, and that's going to give you your pressure drop. If ever you check your entering water pressure and it's lower than your leaving water pressure, then your flow is going backwards. Or for some reason the unit is mislabeled. That has happened a few times, but normally you've got the flow reversed. It's not the end of the world, but we don't get good turbulent flow if we run it through there backwards. So you'll notice a little bit of performance drop if you were to run it backwards. So water pressure drop in feet ahead, we don't really use feet ahead. That's more for sizing of a pump. So if you need to size a pump for a 4,000 foot loop field for this amount of feet ahead, then you can also add in your feet ahead for the unit as well to make sure that your pumping is where it should be. Your pump will be big enough to flow through properly through the system. Entering air temperature, that's your return air temperature on the unit. If you've got a water-to-water unit, that'll say entering or leaving load temperature. But for the air side of things, we look at entering air temperature. We do have a correction factor, so if you're outside of those ranges, in the back of all of our manuals, there is a correction factor you can use. I don't normally use the correction factors unless my numbers are off a little bit. So again, entering air temperature on your ductwork there. So again, if it's 65, here is the cooling factor correction chart, and you can just do the math. Normally we have 80-degree return air temperature in cooling and 68 in heating, which is normal for our industry. The heating capacity, okay, so heating capacity you will see is a higher number than what is next to it, the HE, the heat of extraction. So heating capacity is basically you have what's called heat of compression in a system. So you have the heat of the electrical components in the system that we have to do something with that heat as well. So basically, in this example, let's say we're pulling 30,000 BTUs out of the loop field. There's also, we're just going to say 10,000 BTUs of heat of compression in the refrigerant circuit that we've got to do something with as well. Well, in heating mode, we just pick up that heat and we take it into the home. So we've got 30,000 BTUs from the loop field. We've got 10,000 BTUs from the heat of compression. So actually what we're heating the home with is our heating capacity, the total heating capacity, which would be the 30 plus the 10, which would be 40,000 BTUs. It was what we're actually putting into the home. So we can actually figure out what the heat of compression is. There's a calculation for that, and that's volts times amps times your times your efficiency of your compressor equals watts. So volts times amps equals watts. So if we were to take, 240 volts times 15 amps, that's gonna, and multiply that time a correction factor. Normally a compressor is about 90 to 95% efficient. So we can take that number that we got from our amps times our volts, multiply, I just usually use 0.9 because it's easy, which is 90%. And then that'll give you a number. And that's gonna be the amount of BTUs that you're gonna add to your extraction for your total heating capacity. With that number, we can also figure out your COPs and your EERs and how efficient the unit's actually running. But we do list heating capacities in there. Heat of extraction is just that, what we're pulling out of the loop field. So it's the amount of heat that we're extracting from the loop field. And that's what we're kind of going to cover today. Leading air temperature is the supply air temperature to the home. So you can see, if you look at this chart on the very top one, at 30 degrees, 60 degree entering air temperature, the leaving air temperature should be roughly 83.3. So about a 23 degree temperature difference. We're normally somewhere in that range on the air side of 20 to 25 degrees. Again, leading air temperature is your supply air temperature coming out of the top of the unit. Input, that's your power input in kilowatts. And that's your BTUs. That's your heat of compression. So once we get basically our kW, then we can multiply that times, I just forgot what that actually is. They'll probably show it here in just a second. But that's our power factor, basically, of the amount of kilowatts, and that's how we figure out our COP, coefficient of performance. So basically, coefficient of performance is how efficient the unit is. Basically, what it is your total heating capacity divided by your the energy it took to make that energy. So we have 10,000 BTUs that we use to make that energy would be our power input. So 10,000. And then we'd have our 40,000 BTUs to the home. So we'd take that 10,000, divide that into the 40,000, and that gives us a 4.0 coefficient of performance. In cooling mode, we use EER, energy efficiency ratio. In heating mode, we use coefficient of performance. Again, coefficient, COP, is BTU output divided by the BTU input. So what you're outputting to the home divided by what it took to make that. So in this example here, if we've got, it's showing us we've got a 3.58 COP on the unit. So we would take our kilowatts and we could do the back math on that and figure out our BTUs, take that 2.47. I think that you have to multiply that times like 3.41. But I totally slipped my mind right off here, but I apologize. If you email me, I'll send you over the actual calculation. We will cover that a little bit more in depth in some startup and troubleshooting procedures, which that'll probably be a training we'll have maybe towards the beginning of May. On the cooling side of things, now we look at basically we've got total cooling capacity, our sensible cooling, our heat of rejection. If you ever looked or ever thought about it, you'll see that heat of extraction is always lower than your heat of rejection. And that's not because the units, can't perform as well. What that is the heat of rejection is your heat of compression. We still have that heat in cooling mode that we have to pick up and do something with it. So we're picking it up and putting it into the loop field instead of picking it up and putting it into the home, which is counterintuitive because we're trying to cool the home. So we're removing heat from the home. So we remove heat from the home, remove heat from the heat of compression, and put all of that back into the loop field. And that's why heat of rejection will always be higher than your heat of compression. But the calculation that we do to get to our heat of rejection is the exact same. It'll just always be higher. So how do we perform the measurements and the calculations? So before a system can be properly diagnosed or serviced, we've got to make sure we've got proper water flow and proper airflow. Airflow, you can look at the ECM board, watch the little blinks, one blink for every 100 CFM, so you can kind of see what your airflow is. Water flow, I guess you can put your hand on a pipe and say, I can feel it moving, but that doesn't tell you that it's proper water flow. So without flow meter tools or pressure gauges, there's no way to know what our water flow is. So make sure we've got those correct tools, and we've got to establish those first. You guys call into tech support, you'll start rattling off refrigerant pressures to us and stuff, and more than likely, we're going to slow you down a little bit, we're going to back you up, and we're going to start from the beginning. I understand maybe you've already checked it, but we haven't. So just when you're on the phone trying to diagnose something with the technicians, sometimes we have to ask dumb questions, what you may consider dumb questions, but we're not on the job, so we don't see it. So don't take offense to anything we ask, but we've got to start somewhere. Troubleshooting on the phone is an acquired talent, I would say. It probably took me, before I really felt comfortable on the phone troubleshooting, about a year. So it just takes us a little bit more to kind of build the picture in our head. So sometimes we're going to ask you questions that you may feel are not relevant, but they may mean something to us. So don't ever think that we're just trying to question your abilities, but sorry, I got off on a little tangent there. These are the tools that you will need. So this is the Dwyer pressure gauge, and maybe I should move this picture to more the beginning of the training. I'm not really sure, but we're covering them here. This is the Dwyer pressure gauge on the left. To the right, upper right, is the older temperature gauge that we would, or temperature probe that we would use. And then the bottom one is that Cooper, and you can see that it's tapered there at the end. I've got a couple of these, and I've used them. I've had them for about 4 or 5 years, and they're still intact. They've been pretty rugged. I let someone borrow one of them, and they did put channel locks on it and squished it. But other than that, it's worked out pretty well. I think this Cooper gauge or thermometer is like $20, so it's pretty reasonable. And again, it'll slide into those PT ports a lot easier for you. It does have a hold function on here, and it also you can change it from Fahrenheit to Celsius, and it will also show your minimum and maximum temperatures that thermometer has seen since you turned it on. Closed loop systems, anytime you've got a pump and dump or the pressurized flow center, which actually the newer non-pressurized flow centers, we can get proper water flow with pressure drop. Some of the old QTs weren't real accurate with their pressure drop across it, so we really couldn't use it. But with the new NP series, variable speeds and things, those pressure drops will work with PT ports. So make sure you have the PT port, gotta have them. You call in, don't have it, I'm stuck in the mud. We can look at temperature difference, but that doesn't really mean anything because that's obviously going to be affected by the amount of water that you're flowing. So this is basically the opening for the thermometer and the pressure gauge, a little cutaway of it. It's got a little neoprene gasket in there. There is a cap that's got a gasket on it as well. Over time, the neoprene will get a little bit weaker, maybe even, maybe get a crack or so in it. And it may spray out a little bit when you pull your thermometer out. Not a big deal. Just make sure you don't lose the cap, and that'll seal it back up. On a non-pressurized, you can put in a flow meter tool. We have like a 1 through 10 and a 1 through 17 GPM flow meter tool that you can put into the tank and leave it, kind of like a sight glass on a boiler. I would not recommend that, only because water is nasty. And if you guys have worked on boilers or any water systems with a sight glass in it, you know over time, and it really doesn't take too long, it's going to get cloudy or brown, and you're not going to be able to see it anyway. So it doesn't have to stay in. Once you set your water flow on it, nothing should change in the system. So once you set your water flow, you shouldn't have to reset it. And you can also take that flow meter and hook it into the flow center and run the system, and then remove it again once you're done, and then run it without the flow meter tool. One thing that is nice about non-pressurized flow centers, I'm not really going to get into them because we have a training coming up on those, but it is nice because you can add antifreeze real easy to a non-pressurized. The air is obviously separated a lot easier from a non-pressurized system, and you can see the level of fluid that you have in there, so it makes it a little bit nicer. But I have a lot more experience on pressurized, so I like pressurized flow centers, but our systems don't care if they're pressurized, non-pressurized, open loop. They're going to run just the same. So whatever you guys are comfortable with, or whatever is already on the job, is fine with me. I just prefer, just because of experience, the pressurized flow centers. The heat of extraction, heat of rejection formula. So basically it's temperature TD, which is temperature difference, which is between your entering and leaving water temperature. Your GPM, which is the pressure difference between your entering and leaving water, and then convert it to pressure, or to your GPM using our manual. Times your brine factor. Brine factor, or your antifreeze factor, your fluid factor, it's called quite a bit of things. But that's basically found by multiplying the weight of the fluid times 60 minutes in an hour. But that's kind of stupid. I don't think you're going to weigh the fluid and do all that. Basically, the easiest thing to know is use 500 for your brine factor for pure water, and use 485 if you've got an antifreeze and water mixture. So if you've got a closed loop with antifreeze in it, use 485. If you've got pure water, open loop, use the 500. Or if you've oversized your loop, so you're down in Florida and you don't have to worry about water freezing, then you can use no antifreeze in a closed loop. But if you anticipate your water temperatures are going to get to 40 degrees or a little bit below, anything below 40 degrees, you must put antifreeze in our system or in the water circuit, because it will freeze. Anything can happen, a contactor gets stuck, whatever. But at that 40 degrees, you could also be leaving at around freezing. So we want to make sure that we're not freezing heat exchangers. Coaxes can handle freezing tiny bit, maybe a little bit, but a hard freeze, they will rupture. A braze plate, you freeze it once, you might get lucky. You freeze it twice, and I guarantee you won't. Those passageways through that braze plate are real small. It'll swell that braze plate. On that braze plate, you've got a water plate, refrigerant, water, refrigerant, water, refrigerant. So if one of them breaches, you get water in the refrigerant circuit and the compressor's toast, the unit's trashed. So make sure that if you think that it could freeze, that you're putting antifreeze in it. Antifreeze capacities, I'm not really going to get into this a whole lot, but they will give you the exact capacity factor or your brine factor over here to the right for every single one. But you'll see like 30% propylene glycol is 483, so only 2 points off of our 485 that we normally use. And you can see methanol's got 490. But so if you really wanted to use the exact calculation or the capacity brine factor, you could definitely pull up this chart and use it. But for our sake and simple calculations, we just use the 500 for water and 485 for an antifreeze mixture. So if you ever looked at our manuals, you'll notice that we have 3 flow rates listed on the manual. So don't just choose one and say, that's what I'm moving. They have a meaning behind them. Now, if you're in full load and you're running 2.1 pound pressure drop at 30 degrees, yes, that's going to tell you you're moving 6 GPM. But that 6 GPM, now we're looking at, this is a YT unit, so it's a packaged 4-ton unit. Now, I told you we recommend on a closed loop 3 GPM per ton and 1.5 on an open loop. So these flow rates, that's the minimum flow rate for an open loop. So a 4-ton unit, 1.5 GPM per ton would be 6 GPM. So minimum flow rate for an open loop system is what we're showing there. The next flow rate is a minimum flow rate for a closed loop. We can go down, if we have to, down to 2.25 GPM per ton. That's the minimum we can go. We would prefer you're at 3, but if you're at the edge of a pump curve and you don't want to add another pump and you can get 2.25 GPM, we're okay with that. Just don't go any lower than that on a closed loop. The third flow rate is the recommended flow rate on a closed loop, so 3 GPM per ton. So that's what we're looking at on our flow rates. So we'll do a little quick flow rate example. So if we've got a YT 048, 30 degree entering water pressure, 40.8 PSI in and 36 out. So 40.8 minus 36 is 4.8. So if we look in a chart, 4.8, we take the PSI, not the feet ahead, take the PSI pressure drop at 30 degrees, and that tells us we have 12 GPM. So don't just guess that you've got 12 GPM going through there. Do the pressure drop so we know that what we've actually got. Obviously, again, PSI out should always be less than PSI in. Obviously, pressure drop, there's your 40 and your 36, that would be your 3.4 pressure drop. Make sure that your pressure in, again, is lower than your pressure out. Then you'd look at your chart. You'd find your 30 degree entering water temperature, your 3.4 PSI pressure drop, and that tells us that our unit is moving 7 GPM at 30 degree, 3.4 pound pressure drop. That's why it's so important to have these manuals, because without them, you're not going to know what your GPM is on a pressurized system. Temperature difference, I'm pretty sure you guys can figure out how to do temperature difference. We do it on air quite a bit, but basically entering water temperature at 36.8, leaving at 31.2, and you do the math. So 5.6 degree temperature difference in this example. So we'll go through some examples of heat of extraction, heat of rejection. Here's an XT048. Again, make sure we're in second stage, closed loop. We've got entering water temperature of 52.1 and leaving water temperature of 44.9. Now, normally when you guys call in, you give me temperature differences. The normal temperature difference you'll have on a system, if it's a closed loop, you're normally going to have between 5 and 9 degrees, depending on flow rates. In cooling mode, it'll probably be more like 6 to 8. But again, depending on flow rates. But so you can kind of look at your temperature differences when you first take them and kind of say, well, yeah, that seems probably, might be good as long as we've got good flow. So once you guys start doing more heat of extraction, heat of rejection, you'll start to see things and, notice, hey, I bet this calculation is going to work out, or, so as you work on it more and more, you'll get more comfortable with it. So we take our entering water pressure next. I don't care if you take pressure drop first or temperature difference, it doesn't really make any difference. But here we're doing pressure drop second. So we've got 52.4 in, we're leaving at 47.6. So we just do the math and that gives us 4.8 PSI. So I'm going to tell you that once we look it up in the chart, that's going to tell you that it's 12 GPM. So we've got the numbers that we need. Now we just run the math. So we've got our temperature difference of 7.2 times our GPM of 12 times our brine factor. And we've got a closed loop. So we're assuming that you've got antifreeze in there. So multiply that times your 485. That gives us 41,904 BTUs. That's really just a number. I mean, you can say, yeah, on a 4-ton unit, that sounds like it might be all right. But we have to look at the manual. If you don't have a manual, call me. I'll look it up for you. Take me 2 seconds. We'll look it up and I'll tell you yay or nay, whether it's good or bad. So if we look in the manual, XTO48 at 50-degree entering water temperature and 12 GPM, it tells us that we should have 40,100 BTUs on our heat of extraction. So as long as the number that we calculated, the 41,904, is within 10% of what's in the manual, there's no need to put refrigerant gauges on the system. There's no need to really do anything else. That unit is doing all that it can. So as long as you're within 10% of what's in the manual, you're good to go. We'll go through a few practice exercises together, and we'll look at the charts and kind of go through them, and then we'll probably open it up for maybe some questions or go through some more examples. We'll kind of leave it up to how you guys feel today. So in this exercise, we're going to assume that we have 1600 CFM. The manuals will show CFM levels, so it doesn't really change. When we get to the manual, I'll kind of explain it a little bit more, but it doesn't really change the BTUs a whole lot. So a lot of times I don't look at that unless my calculation is outside of my 10%, then I might go back and look at that kind of thing. But a lot of times I don't really look at the CFMs right off the bat, because a lot of times I don't open up the door, to the lockout board to look and see what's flashing. I just start going, checking pressure drop, checking temperature, and going from there. So we've got a YT unit 048, so we got a packaged unit 4-ton. Our brine is methanol. So we've got entering water pressure of 49 and a leaving water pressure of 46. Pretty easy to do the math on that. 3-pound pressure drop. So we'll make a note of that. 3-pound pressure drop. Go ahead, while you're there, go ahead and do your temperature difference at the unit. So we have 53.5 in and 44.6 out. So in this example, if we've got 53-degree entering water temperature and 44-degree leaving water temperature, what mode of operation are we in? Well, we're in heating mode, because we're extracting heat from the water and putting it into the refrigerant in that heat exchanger, in that coax that's right there in that picture. So if you're in heating mode, your entering water temperature will always be higher than your leaving water temperature. And in cooling mode, your entering water temperature will be lower than your leaving water temperature. So in this example, we have an 8.9 degree temperature difference. Sounds pretty good. again, we're in heating mode, brine factor of 485. We have a 3-pound pressure drop at our 50-degree entering water temperature. So this is where we're going to pull up the manual. We're going to go to obviously the correct tonnage unit. We'll come down to the 50-degree entering water. We are really at 52, but 50 is close enough for what we're trying to get into. We had a 3-pound pressure drop. So 2.9, that's pretty close. I mean, a 0.1, I'm not really too worried about that. A lot of times you'll see if you've got a digital pressure gauge, it'll kind of bounce a little bit on the pressure gauge. So you will have to kind of extrapolate the information anyway. So as long as you're getting relatively close, you should be pretty good. But 2.9-pound pressure drop at 50 degrees is 9 GPM. That minimum flow rate, which in turn is why you see a little bit higher temperature difference of roughly 9 degrees. Again, the slower you flow the water, the greater the temperature difference. It's in contact with the pipe longer, so it transfers more heat. That's why on a open loop, you may see 16, 17 degree temperature difference, where on a closed loop, you'll see half of that because we're moving twice the amount of flow. Again, so back to where this example. So we know we have 9 GPM. So now we know our GPM, we know our temperature difference. Sorry about that. I need to obviously adjust that slide a little bit. So now we've got all the numbers that we need to measure the performance. So we can just do the math, run the formula. GPM of 9 times our temperature difference of 8.9 times our brine factor or our fluid factor of 485. So 9 times 8.9 times 485, and that's going to give us a number of 38,848 BTUs. Now that's just a number. We're going to have to take that number and compare it to the manual that we just looked at. So we'll look it up in our spec manual. Again, go down to your 50-degree entering water, our 9 GPM, and we had 1,600 RPM, or not RPM, CFM. Sorry about that. So we look at that. We go to our heat of extraction, scroll down, 1,600 CFM, 39,600 is what that means. That 39.6, that means 39,600 BTUs is what the unit should be doing. So now we know what we measured, 38.8. The catalog's at 39.6. So are we within 10% of what the catalog recommends? Yeah. Yeah. We're actually probably moving a little bit more than the 3 GPM, or the 9 GPM. We're probably moving about 9.5 GPM. And that would probably put us right at the number because we are actually at 3 and not at 2.9 on our pressure drop. But this gives us close enough. 10% of 38,800 is about 400 or about 4,000 BTUs. So as long as we're under or over 35,600 BTUs, then we're within our 10%. So yes, this unit is operating properly. We'll go through another exercise here. We're going to assume 1950 CFM, obviously T 060, so a 5-ton unit. Entering water pressure of 23.5 and leaving at 21. We just do the math. That's a 2.5-pound pressure drop. Go ahead and take your entering water temperature. 48.7 in and 67.9 out. So we got a 19.2 degree temperature difference. That pretty much tells us, if you didn't already know, that this is probably on an open loop system. or you've got a pump that's bad or something. You're not moving enough water flow. It ought to be, make you start thinking about things. Maybe you already knew it was an open loop, so you already knew that it should be that high temperature difference. But if not, that number should make you think. Again, since we've got 48 degrees in and 67 out, the temperature coming in is higher than leaving, so we're rejecting heat. We're pulling heat from the home, putting it into the water, and rejecting it out to the loop field. Our entering water is less than our leaving water temperature. So our brine factor, I didn't tell you that before because I wanted to show you that 19.2, but again, our brine factor is water, H2O. So we're in cooling mode, we discussed that. The brine factor for water, straight water, is 500. We know our pressure drop of 2.5, but we don't know our GPM. So we know our entering water temperature is roughly 50 degrees, and we know our pressure drop. So we'll go back to this to the manual. We've got 50 degree entering water temperature, a 2.5 pound pressure drop. Sorry, I need to move that circle over. Sorry about that. Because we're not looking at feet ahead. We're looking at PSI. So that 2.5 that we had, pressure drop, is equal to 7.5 GPM, right next to it. Flow and GPM, 7.5. So we know our GPM. Our delta T was 19.2. So now we have all the numbers that we need. We've got the manual in front of us. We can just run the math. So we run our GPM of 7.5 times our temperature difference of 19.2 times our 500 on our brine factor because we're not using antifreeze. So 7.5 times 19.2 times 500. 72,000 BTUs. Again, that's just a number. We'll have to look it up in the spec manual. Again, 50 degree entering water temperature, 7.5 GPM, 1950 CFM. So that tells us 80, actually it's supposed to be 80,400. I think when I adjusted these to the lengths, it kind of threw that off a little bit. I apologize. So it should be 80,400 BTUs, 1950 CFM at 7.5 GPM. So we know that number now. We actually measured 72,000. The catalog was at 80,400 BTUs. So 10% of 80,000, even if it's 100, let's just say, would be 8,010 BTUs. So really, we are within 10% on this unit. We're right on the edge. In my recommendation, I would probably look back. I mean, if this is the first time you've been out there, you may want to just make a note on this unit that it's right at the 10% and to recheck it when you come back out. If you're there because they say the unit's not keeping up, you may want to dig into it a little bit deeper. But if you're just there for a service, I really would just make a note and say, make sure we check our rejection the next time we're out and make sure it hasn't dropped further down. In a situation like this, it could be that the heat exchanger is starting to get a little bit scaled up and it's not necessarily ready to be cleaned yet, but it will be next year. So that's probably what I would look at. We actually have a way also, I'm not going to get into it today. It'll be something that we cover in troubleshooting and startup in 3 or 4 weeks. But we do have a calculation that we have that we can figure out if a heat exchanger is scaled up. We can take some pressure ratings and some temperatures and do some math. So that is available if you ever want to figure out on an open loop if your heat exchanger is starting to scale up. We have a calculation. We'll cover that at a further training. But again, with this one being right on the edge, as long as there's no problems with the unit keeping up, I wouldn't throw the refrigerant gauges or anything on it. Just make a note to come back and look at this at a later date, you know, next year when you have to service it again. So we'll go through and go ahead and do another one here. I think we've got maybe 2 more. This is a 3-ton unit, a YT packaged unit at 1240 CFM. And we're using glycol in the system. So we've got entering water pressure 18, leaving at 15. Pretty easy to figure that out. 3-pound pressure drop. Take our water temperature difference of 30.1 and leaving at 26.9. So 3.2 degree temperature difference. It seems a little low, you know, just looking at the temperature difference. But you can't just assume. We all know what that means. So we still have to do the calculations, but it just makes you start to think before you have all the info. It makes you start your brain start working. So we know our temperature difference. We know we're in heating mode because our entering water temperature is higher than our leaving water temperature. The brine factor for antifreeze, in this case being glycol, it's going to be 485. So we know our pressure drop was 3. We'll go ahead and pull up that manual again. Let me go back. We had 30-degree entering water temperature and a 3-pound pressure drop. So 3.2 is pretty close. So that tells us we're moving the right amount of water flow. But we saw that 3.2, so you're still starting to think in your mind, 3.2 seems kind of low on our temperature difference. So we'll go ahead and we'll run the calculation. 9 GPM, delta T of 3.2. So we run 9 GPM times our 3.2 times our brine factor of 485. And that gives us 13,968 BTUs. We take that number and match it to what's in the book. Again, 30-degree entering, 9 GPM at 1240 CFM, 22,700 BTUs. Well, 10% of 22,700 is about 2,770 BTUs or 700 BTUs. So we're within 10%, a minimum of about 20,000 BTUs. And we're at 13. One thing that I would say on this example here, obviously it's not operating properly. So before you throw your refrigerant gauges on there, what I would look at is this is a 2-stage unit. We're running about 2/3 capacity. So maybe the unit's not shifting in the second stage, because when we run in second stage, we run when we run in first stage, we run 2/3 capacity. The other third comes in when we switch to second stage. So this might be something that the solenoid on the second stage is not working, or the thermostat's not giving us a Y2 signal. So that's the first thing I would check. If you are in second stage, then we'll have to go ahead and move on to the refrigerant side of things and look at the refrigerant pressures. We know we've got good airflow. We know we've got proper water flow. So it has to be in the refrigerant circuit somewhere. We do have a heat of extraction rejection video on YouTube. So again, you can subscribe to us on YouTube. There's a video on there you can sit through and watch. This training will be on there as well. This training, the video is actually done by our old trainer, Jeff Johnson. He's actually pretty good. So, you know, feel free to watch it there. That is basically all I have as far as content. So if there's any questions or anything, you know, feel free to ask them now. If you think of something after the fact, shoot me an email, give me a call, talk to any of the guys in tech support about it. if you want handouts, practice exercises, anything like that, I can send those over to you as well. But I appreciate your guys' time today. And, if you guys have suggestions of trainings that you want me to do as a webinar, shoot me an email. I'll definitely put something together and put it out there. The worst thing that happens with these webinars is nobody signs up. It's not like I'm traveling to California to do a training and nobody shows up with a webinar. I can just reschedule. So, I don't know if your take from some of the technicians in the field is, but again, feel free to reach out to me with anything, and I really appreciate your time, and have a great day, and stay safe and coronavirus free if possible. Thanks again, and have a great day, guys. I'll stay on here for a few if you got any questions. All righty, if that's all we have, we will adjourn. I look forward to training you guys again soon.